Good afternoon, everyone. I'm Angela Austin, the Challenge Program Manager at National Security Innovation Network, or NSIN. It's my pleasure to welcome you to the Global Fishing Forecast Challenge pitch event, presented by NSIN and in partnership with National Geospatial-Intelligence Agency. Today, we convene to address a critical challenge, forecasting maritime vessel traffic involved in illegal, unreported, and unregulated fishing. With the support of our esteemed partners and the dedication of our subject matter experts, we embarked on this journey when the challenge launched back in January. And our goal is to identify innovative solutions that can inform U.S. and partner nations' responses to IUU fishing. The mission of NSIN is to drive national security innovation by fostering collaboration among diverse communities, including universities, researchers, students, entrepreneurs, and ventures. By connecting innovators and facilitating partnerships, we aim to develop technologies that directly support those who are responsible for protecting our country. And before we proceed, I just want to briefly outline today's event flow. We'll kick off with opening remarks from NGA, followed by pitch presentations from our 10 finalist teams. Each team will have 5 minutes to present their solution, followed by 5 minutes of private Q&A with our judging panel. And during the private Q&A, you are welcome to take a quick break before we proceed into the next pitching team. And then finally, we will wrap up with closing remarks. So a warm welcome to all participants, judges, and guests joining us today. Thank you so much for being part of this important initiative. I'm excited for an inspiring and productive event. Without further ado, I'll hand it over to Mr. Tom Vashik.
Hey, good afternoon, everyone. Thank you, Angela. So my name is Tom Vashek. I'm the lead for Director for Strategy, Partnership, and Communications at NGA Research and Development. So we are the research development component of NGA, and we are also the sponsors of this challenge in partnership with NSIN. So I don't want to take too much time. I want to jump straight to the pitches. But really, on behalf of NGA R&D and really all NGA at large, I really want to start off with congratulating all the teams for your selection to phase 2. I know it's been a lot of work and daily work and some probably laborious work to get here. So I just want to say really appreciate your dedication and just some of the great things you've put together to enable this movement. So just as you know, IUU fishing is just an incredible challenge from a geopolitical, diplomatic, economic, and environmental perspectives to the really the international community, and particularly to the U.S. government. It's something we're really trying to get after as an agency. We are looking obviously at how we can do detection. That is a key element of it. But to some extent, detection is almost too late. By the time we catch the ships, find the ships, transmit data on them to our customers, either locally in NGA or elsewhere in the government or even as partners, it may be too late. And that really leaves us with an opportunity only to almost name and shame and just be smarter for the next time. So really what we're trying to do here is what can we do with forecasting? How can we push the state of the art of forecasting in the maritime domain awareness, even if it's not 100% level, to help us make better use of our sensors so we can point them in the right direction where we expect them to be? How can we use them to inform the disposition and the deployment of any kind of law enforcement, interdiction capabilities, just to really get ahead of this problem? As the R&D element, we know this is hard. We know this may not be perfect, but we are really, our job is to really push the state of the art and see what we can do. And I think the commercial industry, particularly with the focus and availability of new unclassified data sources, is going to be key to that. So with that, I just want to again reiterate how important this is for us, both at NGA and the USG, but certainly for the R&D and the forecasting world. So again, really looking forward to seeing your team's pitches and obviously continuation of looking at the forecast. So with that, welcome again and congratulations.
Thank you, Tom. And with that, we'll go ahead and get started with our first team, JetAware.
Hi, I'm Ben Johnson. I'm the Chief Scientist of JetAware Corp, and I'm going to be presenting work that I did on the GF2 challenge with my colleague Ezekiel Barnett. JetAware Corp is a small business that does a bunch of work across a pretty wide variety of domains: machine learning, climate science, remote sensing, etc. But Zeke and I are machine learning people, and we thought that the GF2 challenge was really interesting from that perspective. At a high level, our approach was to train deep neural networks for spatiotemporal forecasting of global fishing effort. You may have seen in the media coverage of these generative AI models that can generate very realistic images or videos. And you can imagine conceptualizing the GF2 forecasting task as very similar to a video forecasting task, where you think about the historic data as a video of fishing activity, and the goal is to predict the next few frames. We adapted these kinds of video models, these sorts of architectures, and successfully built a powerful forecasting model for the GF2 task. We trained it on as much global fishing watch data as we were able to get our hands on, over 10 years of global coverage data. And our model demonstrably outperforms baseline methods, which is actually harder than it sounds because this is a very difficult forecasting task. And our model is also relatively agnostic in the sense that it could be retrained to either consume or produce different kinds of data pretty easily. Going into more detail, we trained an autoregressive UNet style deep neural network to do this task. These architectures have been proven through their use in models like DALL-E and Stable Diffusion to be capable of learning complex nonlinear dynamics. And that's exactly what we need to be able to do if we're going to forecast fishing effort accurately. Shown on the upper right, our model takes a stack of frames of past activity and produces two output maps, one fishing likelihood in a particular place and the other fishing quantity in a particular place. Now, the forecast specifically asked us to consider novel data sets. And so we teamed up with some folks at the MIT Oceanography Department and WHOI and talked to actual expert fishers about how they determine which spots to go to. They, of course, use topographic features like whether there's a shelf or not, but they also use a variety of remote sensing products such as sea surface height and sea surface temperature to determine where to go on a given day or week. We thought about these exogenous variables a bit and basically determined they come in two flavors, slow and fast changing. A slow changing variable is like topography. And if that impacts fishing activity, that impact should be visible in historic fishing activity, and the variable itself may be redundant. On the other hand, fast changing variables like sea surface height and temperature may themselves be very difficult to forecast on the 3 to 5 week time horizon. And so it's hard to use those in our models as well. We don't have high fidelity physical forecasts of those sorts of things, but we do think they're an interesting avenue for future exploration because we know that fishers do use this sort of data to determine where to go. And there's no reason to think that IUU fishers aren't using this sort of data as well. Another small innovation in our approach was to directly optimize the challenge metrics. We started off using traditional video prediction loss functions, and they give very interesting results, sort of realistic samples of what the next frames might look like, but they don't score well on the challenge. And so we switched the loss functions, and I mention this just to say that in the design of a sort of machine learning task, the scoring metrics and how you measure them can really have an outsized impact on the actual behavior of the model. So that's a very important thing to consider. Finally, the benefits to the US government. I think specifically, our models can be used to predict fishing activity. I think by adding additional data modalities that we did not have access to during the challenge, such as synthetic aperture radar data, dark target data, or these sort of high fidelity forecasts of oceanographic data, we could extend these models to work well on IUU fishing. Stepping out more generally, because our methodology is data agnostic, it's not fishing specific. It could be applied to other civil and military geospatial forecasting tasks, of which there are many. And finally, from a research perspective, we really do think that building on top of these really successful video generation models and adapting them to do complex geospatial forecasting is potentially a very fruitful research topic, especially in situations where you want to be able to simulate a diverse population of potential future trajectories rather than just sort of the middle best guess. That's my presentation. Thank you very much for allowing us to participate in this demo day, and have a good day.
And next we will hear from Allen Institute for Artificial Intelligence.
Hello, my name is Joe, and I'm a senior product manager for Skylight at the Allen Institute for Artificial Intelligence. Skylight's a maritime domain awareness platform that provides watch standards operators, analysts, and protected area managers all around the world with a near-time tool to identify suspicious vessel behavior and take action. We apply state-of-the-art AI, such as computer vision and machine learning, to a combination of data sources. And we do this to accelerate the way that organizations make operational decisions critical to protecting our oceans. I'd like to share insights from our approach to the fishing forecast, which has become a critical part of our roadmap in our ongoing efforts to counter illegal, unreported, unregulated fishing. The big challenges of this task are that the training data is sparse, limited, and composed of very incomplete time series, and it's based fundamentally on the outputs of a machine learning model. So to deal with these challenges, we actually developed an ensemble naive seasonal model, and this delivers very robust, generalizable, and explainable assessments of expected fishing activity over the next few weeks, or in fact, over the next year. We selected this approach based on the highest performance on competition metrics after an exploration of alternative algorithms. The other advantage is that it's trained extremely quickly and efficiently, and it's extensible to any of the sort of maritime events and trends that we monitor and detect, such as vessel detections and imagery and encounter events between vessels at sea. It matches the intuition of our maritime experts. Fundamentally, geography, the bathymetry, distance to shore don't really change on human timescales. The relevant ocean conditions tend to be very forecastable in typical cycles and don't change rapidly. These include sea surface temperature, surface anomaly, and salinity. And conversely, though, human decisions are very complex, but also guided by habits. And so that allows us to leverage the data that's available in the history to make pretty accurate assessments about where fishing will occur in the near future. And most importantly, these are very useful assessments at the 0.1 degree bin level and the 1 week interval. This allows us to make assessments that are directly useful for patrol planning and ordering imagery in advance. So the strategy is actually fairly simple. So the process of arriving at the ground truth data is fairly generative and complex. It involves the phenology of fisheries. It involves human responses and decision-making to where fish might be expected to be. And it's further biased by the collection of AIS data. So it's a limited, biased, focused set of data collection. This is then processed in turn by neural nets, which by their very nature are never perfect in their assessments, subject to variability, data drift over time, incomplete information bias in the training and labels. But nonetheless, using a fairly simple seasonal approach to, based on previous year's activity at that time of year, make an assessment of where fishing and when fishing will take place. We have seen fairly good and useful metrics of performance while avoiding things like overfitting, data drift, and allowing interoperability with other systems, other approaches. And the solution is not just theoretical, it's very practical and actionable. We've Dockerized the model in the pipeline for seamless deployment in any sort of environment, but we've also placed it on our product roadmap and plan on including it in our platform for integration and delivery to our global set of users. And our journey at Skylight never ends with model development. It's a continuous cycle. We're always improving and refining. We're deployed in over 70 countries, various regional and international organizations, and we actively solicit feedback, iterate on our methodologies, and we augment our deep learning models that were already deployed with high quality annotation of large data sets, user feedback, and CI/CD practices in our development and integration. I want to really extend my thanks to the competition team and sponsors. Their work has really served as a catalyst to explore capability that we had previously only speculated about, but is now incorporated into our product roadmap, and we believe is going to provide real value to our users to assist in counter IUF efforts worldwide. I, of course, want to also thank my collaborators on this project who volunteered their time away from their typical duties at the Allen Institute, in particular, Jenna Sparks, Henry Herzog, Patrick Beckema, who in this phase have really committed a great deal of time to exhaustively explore the possibilities and potential of this capability. And thank you so much.
Now let's turn our attention to PeerSight.
Hi, I'm Bella from PeerSight, and we're on a mission to eradicate IUU fishing and provide persistent maritime surveillance and visibility to the world's oceans. the U.S. Coast Guard has said illegal fishing has outpaced piracy as the top global maritime security threat. To surgically address this, we have developed our platform, Precog, where we seamlessly integrate real-time and historical data from diverse sources like AIS, synthetic aperture radar, climate, phytoplankton, and demographic data, which has shown a 50% increase in accuracy compared to just using AIS. Utilizing these diverse datasets available to us, we construct a space-time cube, a unified and scalable representation of the data. This cube serves as the foundation of our advanced forecasting model. By inputting the space-time cube into our curve fitting model, we derive invaluable insights into maritime vessel traffic. Our system tracks apparent fishing, identifies instances of illegal and unreported fishing, and flags any suspicious activities, making it intuitive and efficient for users. Adding depth to our approach is our focus on integrating demographic data. Recognizing that fishing efforts are primarily driven by demand rather than supply, we then consolidate our data into spatial temporal bins within a space-time cube, where each bin represents 1 square kilometer area at a specific time. This cube not only facilitates efficient scaling with the addition of more data sets, but also avoids exponential model growth. This allows us to grow our data sets with a variety of different types and enables us to analyze fishing activity patterns at a remarkably granular level. Our predictive modeling incorporates Bayesian networks, unraveling the relationships between environmental factors, fishing behavior, and social dynamics. Furthermore, we integrate synthetic aperture radar imagery to identify marine activities even in challenging conditions like cloud cover or darkness, significantly amplifying our ability to detect illegal fishing activity. Leveraging these diverse data sets, our advanced forecasting model demonstrates a remarkable 50% increase in accuracy. Ultimately, these efforts are to aid and benefit the US government to optimize coverage for US Coast Guard vessels around the world, from Guam all the way to San Juan. NYPD has more officers than the entire US Coast Guard to cover more than 95,000 miles of waters with only 2,000 vessels. But our tool turns vast oceans into manageable seas. We do this by providing insights to potential threats and enhancing the overall security of maritime borders and infrastructure. With real-time updates of fishing activity and future forecasting of hotspots in fishing, law enforcement agencies can efficiently allocate resources to monitor and enforce regulations. This proactive approach helps in deterring illegal fishing practices and ensures compliance with maritime laws. By predicting fishing patterns, our tool assists in sustainable management of marine resources. It enables policymakers to implement targeted conservation measures and mitigate the risks of overfishing. This ultimately safeguards the long-term health of marine ecosystems and reduces food scarcity as a whole. And accurate forecasting of fishing activity benefits commercial fishermen also by providing valuable insights into optimal fishing locations and types. This promotes efficiency in the fishing industry, leading to an increased productivity and profitability. Additionally, by ensuring compliance with the regulations, our tool fosters a fair and transparent marketplace, facilitating smooth commerce and trade operations in the maritime sector, so that the legal fishermen can actually come out on top. With the integration of Precog and PeerSight satellite constellations, the US government is set to eradicate illegal, unreported, and unregulated fishing. Our advanced forecasting tool will enable precise monitoring and enforcement, ensuring the protection of maritime ecosystems and sustainable livelihoods. Thank you for your continued support and commitment to safeguarding our oceans.
Moving forward, we will hear from Sinclair.
Thank you for the opportunity to speak with you today. I'm John Sinclair. I'm the founder of Sinclair. My background is in software engineering. My entire career, I've been building analytical tools for various types of analysts in the military, law enforcement, and intelligence communities. The inspiration to start Sinclair came from my work experience overseas. I was the lead software engineer in theater for the U.S. Army's Distributed Common Ground System, Fusion Brain, I work directly with military analysts to design and deploy new geospatial analysis capabilities that worked across multiple data feeds. Sinclair has been an opportunity to expand on that work and continue to solve practical problems. We are presenting our location prediction framework. This capability consists of modular components that can be extended to work with new types of data sources and incrementally improve forecasting algorithms. The import mechanism, shown in blue on the left, is an expandable list of import processors that transform data into a normalized data model that ensures comparability between data sources. The normalized data model consists of 4 different parts: the historical baseline, which is based on ground truth, its probabilistic models for various calendar periods that are used as a forecasting baseline, raw vessel tracks imported from multiple sources that can include AIS, SIGINT, COMET, ELINT, and satellite imagery tracks. Anything that generates location coordinates, and we can accommodate many different types of geospatial representations. Fused vessel tracks are the output of fusion algorithms that aggregate data representing each vessel's locations. The vessel track fusion engine is a critical component that can aggregate the location coordinates from different sources into distinct vessel tracks that can be used in acquiring predictive insight. This component represents, or predictive insight represents any data that can influence future vessel track projections. I will explain this component more on the next slide. The forecasting engine on the right in blue contains an expandable set of algorithms that use the normalized data model components to create vessel track projections and generate forecasts for each region. It is configurable and automated so the output can be wrapped into a forecast API hosted by GFW, which is displayed in green. The orange feedback system is a set of visualization and evaluation tools that can allow algorithm developers to quickly understand the impact of changes as algorithms are adapted. Each model component can be visualized at every stage, which really helps in the adaptation process. We developed a historical analysis baseline to include calendar-based probabilistic modeling with fishing effort data from GFW as the ground truth. The configurability of the framework made it very simple to change to different regions and time periods, and the framework efficiency allowed for quick iterative development, and the visual feedback and evaluation tools resulted in rapid hypothesis testing and optimization. Using these methods, we were able to detect the ground truth errors that began on January 26, well before our first forecast submission. We explored the introduction of vessel-specific projections based on history, and it has shown that it will incrementally improve forecasts. The predictive insight is a method of obtaining and processing information that can help guide predictive analytics by focusing on human factors. We can use the location history of each vessel to perform reverse location searches of social media data to identify crew members of each active vessel. We can then search crew member accounts to find scheduling information through family plans, port visits, and other contextual information. This technique can also be used with advertisement identifiers and comment sources. This project establishes an efficient, sustainable, and replicable location prediction framework for any object classes that move parallel to the Earth's surface over time. This framework allows the government to measure the impact of an approach before committing resources to scale the technique. The visual feedback system emphasizes human comprehension and narrow problem space definitions. This significantly lowers the cost of training AI ML models and increases their effectiveness. Our novel reverse location search technique can identify crew of dark target vessels. Identifying just one crew member can have a tremendous impact on investigations. Thank you for your time. We welcome the opportunity to apply our location prediction framework to your specific CONOP.
Next up, we'll hear from Athenium.
Hi, I am Dr. Ellen Cousins, Chief Science Officer at Athenium. Along with my geophysical data science team colleagues at Athenium, We have determined that predicting fishing activity within the contest regions can be accomplished using an iterative ensemble forecasting approach, which I'll briefly walk you through. Step 1 of Athenium's process is to collect historical fishing data from the Global Fishing Watch and catalog and filter it using the metrics of calendar day, day of week, week of year, lunar phase, and recency to form two-dimensional grand ensemble members capturing various periodicities. Step 2 creates region-specific ensembles based on this filtered data, with approximately 100 ensemble members for CTMFM and 600 for each of the other two regions. Step 3 identifies individual features and computes median values of fishing activity targeted to cells filtered by occurrence count thresholds. This forms Athenium's background forecast for Step 4, which performs well statistically, but is somewhat overly smoothed. Step 5 of our process adds mini ensembles to the forecast, introducing variability in line with historical data. Step 6 intersects the forecast with biological and physical maritime datasets sourced from the open source European Union Copernicus Marine Data Store and Athenium Analytics proprietary tropical cyclone model. This integration masks areas where fishing activity is unlikely, considering factors such as low oxygen content, low net biomass productivity, high wave height, or predicted tropical storm force winds. Finally, Step 7 computes two-dimensional geospatial raster geotiffs of this final fishing forecast. So on the previous slide, I walked through the solution Athenium has developed for this challenge. We verified this methodology through correlation analysis and through hundreds of automated sensitivity tests, resulting in a 2024 average Cohen's kappa of greater than 0.15 and a mean absolute scaled error, or MACE, of less than 0.9. Athenium can apply the existing framework to a combination of real-time AIS data feeds, any government-provided dark target data, and SAR vessel detections to assess the likelihood of IUU fishing by comparing the detections against legal AIS-derived fishing activity. We can also use clustering techniques to compare new detections against known vessel-level behavior to determine fishing activity types, such as trawling, long line, or purse seine. Athenium's methodology is also directly scalable for future efforts to introduce new predictive factors, such as additional social or marine influences, and new techniques, such as machine learning algorithms and ensemble weighting. All the data sets that Athenium used have global coverage, and the model inputs are all scalable to season-long forecasting, using, for example, longer-term model outlooks and climatology analyses that capture seasonality and periodicities. Athenium's approach to the Global Fishing Challenge analyzes and reports on the threats posed by IUU fishing in a way that is scalable and that can integrate new data streams in a versatile and source-agnostic manner. Athenium's use of ensemble modeling in particular enables us to provide probabilities and tailored risk levels. Moreover, having the capability to augment our assessments with proprietary global weather intelligence and computer vision technology, Athenium's assessments can both identify current hotspots and visualize changes to the geophysical attributes of specific locations. As with all of Athenium's products, the resulting solution and capabilities from this challenge are dual use and will serve not only the geospatial analysts in the defense intelligence community, but also commercial clients across Athenium's markets, such as insurance and supply chain. Thank you for your attention, and we look forward to your questions.
Next up, we will hear from Orbital Insight.
Hi, I'm Kathleen Yee, a computer vision scientist at Orbital Insight, and our team is pleased to present our solution to address IUU fishing. In this digital age, we collect massive amounts of data about Earth and human behaviors, as well as ocean and weather conditions from various terrestrial, maritime, and space-based sensors. Connecting these sources is imperative in order to reflect on real-world behavior and to predict the future. There are a number of organizations trying to use these data to address everything from climate change to shipping route planning. Many of their approaches are dependent on a single source of data, or they are unable to scale to meet the demand in order to provide near real-time global insight. What we need is an analytics solution that can comprehensively address the complex nature of IUU fishing. Our concept of operations leverages Terrascope, a flexible and scalable web-based software tool that enables rapid, efficient processing of diverse global data into actionable insights in various visualizations like heat maps and line graphs. We propose using this platform to combine model results from our Global Fishing Watch-based fishing forecasts with satellite imagery and other sensor data to help forecast where IUU fishing might occur. Because Terrascope flexibly integrates third-party data and algorithms, we can leverage the best existing solutions with our own. Additionally, forecast results can be accessed and shared through our web UI and API. For our methods, we focused on two different modeling approaches for our fishing forecast model. First is a multi-scale linear regression, and second is a convolutional long short-term memory model, or a conv-LSTM. Results from our first model is pictured here for the FFA region in the South Pacific. The top chart shows the spatial forecast and how it aligns frequently with the ground truth, with blue showing the Global Fishing Watch fishing effort, and red showing our forecasts over time. On the bottom graph, we have our total fishing effort represented in a line graph, which again shows how well our algorithm performs. Blue is the Global Fishing Watch, orange is our predictions, and green is the forecast. Our models are able to capture activity at different temporal and spatial scales inherent in fishing activity, but conv-LSTM can learn spatial and temporal dependencies of fishing effort with greater precision with more data. In other words, as we scale up globally over a longer time frame, this model actually performs better. With sufficient data, it can learn hidden insights directly without the assumptions or heuristics needed in the first model. Forecast results from either multi-scale linear regression or conv-LSTM can be continuously refined with ground truth data provided by EO or SAR sensors. The main benefits of our ConOps are a flexible platform that can take various data sources and transform them into novel solutions using deep learning and data fusion at a global scale. Our existing baseline fishing effort forecast can be deployed and easily shared. Then the forecast can be continuously improved through user feedback and by incorporating new data and analysis methods as they become available. After we verify that our main forecasting model performs well enough, our proposed enhancements are the data fusion of the model outputs with EO and SAR imagery, ocean and weather conditions, and calendar dates such as holidays and moratoriums. Currently, we have partnerships with a variety of imagery vendors to supplement the open source data in order to cross-reference the fishing effort outputs with our pre-existing ship detection algorithms. The ability to add these data sources or to try new algorithms allow anyone to swiftly iterate through experiments in order to refine their global forecasts. Since real-world problem exists in an open system and technology is constantly evolving, we need a flexible platform that can best reflect the situation with multi-source data fusion and a quick turnaround time. And that is why using Terrascope is the best option for this challenge. Thank you.
Moving along, we will hear from Esri.
All right, hello everyone. Thank you for joining us today for Esri's pitch presentation for the Global Fishing Forecast Grand Challenge. My name is Austin Clack. I'm a solution engineer here at Esri on our national government team, and I'm joined today by Maxwell Titus, a technical consultant also on our national government team. We're going to begin today with an overview of our concept of operations. I'll hand it over to Maxwell at this point.
So this is our ConOps graphic, which is a high-level overview of our GIS workflow that we use to forecast fishing effort. The two primary things I want you to take away from this graphic is first, this entire workflow that you see was automated using Python and also using some ArcGIS methods that are both widely used and well tested for doing temporal forecasting analysis like this challenge. The second thing I want you to take away from this graphic is that we break our workflow into 3 different phases. The first phase is just acquiring our input data from API sources and transforming it. The second phase is taking that acquired transformed data and turning it into space-time cubes. And our last phase is just taking the space-time cubes and applying a machine learning multivariate forest-based forecast in order to make our forecasts on fishing effort for a weekly and daily level. To talk about some of the nuts and bolts of our workflow, the first thing I want to highlight is our input data. We use 4 data sets in a multivariate analysis, and our first data set is historical fishing effort data that we retrieve from the Global Fishing Watch. This gives us just a historical data just to know where a phenomena is being observed and where fishing is actually occurring. The 3 other data sets we use are bioclimatic variables that include chlorophyll density, sea surface temperature, and wind speed that we obtain from Coastal Watch. What's important to know about our input data is that it's pretty easy to substitute, add, or remove new data sets and maintain the rest of our workflow being the same. So for a historical fishing effort, maybe we want to change that out to be historical fishing effort by gear type. Once we acquire all of our input data, we use a series of spatial joins and attribute joins in order to create a grid layer that's at the spatial resolution we want to forecast for, and an associated table that has all of our recorded values separated by grid cell and by date. With those combined data sets, we use Esri's space-time pattern mining toolset in order to do a conversion from those combined data sets into a space-time cube. For those of you who are not familiar with what space-time cubes are, imagine a 3-dimensional histogram where our x and y axis is space and our z axis is time. Further utilizing Esri's toolset, we're able then to do a multivariate machine learning forest-based forecast that applies a best fit model for each individual cell utilizing all of our combined input data sets. This is able to find the best fit model per each cell. So we're able to find and detect any sort of unique geographic relationships between those data sets that make an even better prediction of forecasting our fishing effort on a daily and weekly level. Our final output is a vector data set that not only has all these recorded values, but includes meaningful statistics, including root mean square errors, confidence intervals, and also, if you see in that bottom right graphic, a graph that shows the performance of our model per each cell with the observed phenomenon versus what our model predicted. At the very end of this process, we just convert our vector dataset into a series of TIFF files for the final submission. I'll now hand it off to Austin to finish out the rest of our presentation.
Thank you, Maxwell. So the way that we're thinking about the benefits of the Esri solution to the US government are really spread across these 4 different categories. To begin with utility, the programmatic approach that was taken in the design of the proposed solution really enables the end user to consider additional variables by defining new queries and data sets. A good example of this would be making use of the Global Fishing Watch API queries. For example, you might be able to query by vessel flags or even gear types to begin to highlight nefarious fishing activity. Maxwell already touched on the innovative components of our approach, but another key thing to take away is that these processes are already widely in practice across the intelligence community. This brings us to commercialization. In addition to our methods already being well established in the intelligence community, the technology leveraged by our approach is pre-existing in the NGA technical stack. Additionally, our Python approach can be set up to run on a scheduled basis, as well as be transformed into front-end operational tools, such as geoprocessing tools and web services. Additionally, end users may dynamically change parameters to meet processing and modeling requirements. Our solution is based on the Esri COTS technology, meaning that leveraged tools are constantly receiving updates and improvements, which will lead to enhanced capabilities on an ongoing basis. Finally, the Esri proposed solution is characterized by its novel analysis, which leverages practical, mature technology. Thank you so much.
Next up, we will hear from the University of Miami Sea Stars.
Good afternoon. On behalf of Dr. Hans Graber and the Sea Stars team from the University of Miami, we'd like to virtually welcome you to our campus. This presentation is unclassified ProPen. The Sea Stars team participated in the challenge consists of Dr. Hans Graber, Mr. Matthew Ward, Dr. Jennifer Fritz, Ms. Frances May, and I am Gregory Podominski. Sea Stars is a commercial ground station at the University of Miami, specializing in synthetic aperture radar. Our staff has diverse experiences and specialties. Today, we'll present our concept operations for satellite radar and AIS data integration in the coastal and maritime domain. Sea Stars developed a system to forecast the location and scale future fishing efforts utilizing a dynamic mode decomposition and Global Fishing Watch acquired data. The model uses modern forecasting techniques, including machine learning, neural networks, and deep learning. Furthermore, our methodology can be expanded globally and temporally while incorporating additional features utilizing CSAR's methodologies and databases, further enhancing model complexity. CSARS utilizes unclassified data sources to enhance our models, such as automatic identification system, commercial synthetic aperture radar, commercial electro-optical and multispectral imagery, and publicly available satellite data such as Sentinel and Landsat. Our methodology allows for flexibility of prediction outputs in several ways, including variable timescales, date ranges, CSARS input data, etc. The below diagram describes the input data sets for the CSARS IUUF forecast prediction. Now, Mr. Matthew Ward will discuss methods and results.
The goal of the task at hand is the 5-week or 35-day forecast of the estimated fishing effort for 3 regional fisheries of interest. To accomplish this task, CSARS tried many different types of machine learning models, including linear regression, nonlinear regression, and different types of deep neural networks. In the end, CSARS decided on a technique from the fluid mechanics field called dynamic mode decomposition. Dynamic mode decomposition extracts dominant spatial temporal patterns from a stack of images. In addition, dynamic mode decomposition is very similar to statistical regression techniques, but is built and optimized for analyzing and forecasting images directly, which makes it optimal for this type of challenge. After the dynamic mode decomposition model was initialized for each of the 3 regions, the model is capable of forecasting well beyond 35 days into the future for each region. On the right side of the screen, you'll see a 1-day forecast on the top image for the FFA region. In the center, you'll see a 14-day forecast for the CTM-FM region. And on the bottom right, you'll see a 16-day forecast for the SWIO-FC region. In the end, it was decided that the dynamic mode decomposition model outperformed all other machine learning models and also a naive baseline model with respect to both of the metrics being evaluated. Additional pre-processing and other machine learning improvements are being evaluated continually.
There are numerous benefits that CSARS has and can continue to provide to the United States government. First, CSARS experts have several decades of experience in maritime surveillance, making us a vital partner in combating IUUF. Furthermore, our diverse staff expertise complements our CSARS IUUF forecast models, as observed on the right of the slide. CSARS conducts all phases of the intelligence collection cycle: tasking, collection, processing after downlinking at CSARS, exploitation, and dissemination, also known as TCPED. CSARS has multiple exclusive agreements with commercial vendors, creating the CSARS pseudo-constellation. CSARS has successfully supported the United States government and DoD with their ComSAR data and analytics requirements. We provide unclassified data sources and solutions that can be shared with partner nations. The proposed IUUF forecasting solution uses a state-of-the-art, data-driven dynamic systems model to predict the location and magnitude of future fishing efforts. As observed on the right of the slide, the CSARS IUUF forecast model complements Global Fishing Watch's fishing effort data with additional unclassified data sources such as sea surface temperature, bathymetry, AIS, fish stock data, SAR imagery, network analysis, and other visualizations. Our model is built around modern forecasting techniques and can be enhanced by adding techniques such as Bayesian deep learning, additional machine learning capabilities, and model complexity, while looking forward to a future with quantum computing. Currently, computational resources are not a limiting factor in our methodology. As demonstrated today, CSARS has extensive knowledge and expertise in applied research and can integrate ancillary input data into innovative ideas and solutions to help improve results and solve complex problems. Thank you for your time this afternoon.
Moving along, we will hear from Reverie Venture and Spectron.
Hi, my name is Anand Patel.
Hi, I'm Mauli Chandramouli.
And we're proud to present Netcast GNN.
Our dual-use multi-domain data analytics platform ingests, catalogs, analyzes, and disseminates intelligence from AIS streams and satellite imagery. Our ConOps for this challenge consists of a graph convolutional neural network pipeline for global fishing forecasts. This ConOps is secure, scalable, and fault-tolerant, built on industry-proven open-source components such as Kubernetes. It is free from vendor lock-in and easily integrates with current customer workflows.
We produce 3 distinct models for the 3 RMFO regions, and their performance is shown above using the MASE score. The overall MASE score is 0.5547, which means about a 45% reduction from the naive forecasting methodology. Below, we have a diagram showing how model iterations improved our MASE score, and I'll walk you through that. Between model 1 and 2, we used a minimal AST/GCN with 100 nodes randomly sampled. Between 2 and 3, we introduced top node analysis for dimensionality reduction, still using 100 nodes. Between 3 and 4, we increased the top node count to 307, which was constrained by compute costs coming from virtual RAM and training time. Between 4 and 5, we increased the number of training epochs from 120 to 300. Increasing computational resource investment through virtual RAM and training time, we can introduce other features to the AST/GCN nodes, such as weekdays, holidays, time of year, and vessel counts that we already have prepared in our pre-processing pipeline. And we can increase the top node count beyond 307, with our next experiments planned to be 1,000 nodes. We employed several aspects to our methodology. We used dynamic outlier correction to cap the fishing hours at every location on every day in the dataset dynamically using data coming from the fishing vessel count. This also segregates part of that data for dark target fishing activity training that'll come in the future. We created several time-based features that we will introduce in the next iteration of our model. Our 3 models can easily be scaled globally, and this methodology can produce new models by passing new regions with their AIS data through the pre-processing pipeline and producing graphs for top nodes in these regions. Regional models are patchwork compiled together for inference to produce global forecasts. Our top node analysis identifies key areas in a region based on historic fishing activity, similar to PCA for dimensionality reduction, and including more nodes asymptotically describes 100% of fishing activity. This is constrained by resources. Using a subset of top nodes reduces computational costs and focuses on important subregions and often generalizes better. We innovatively cast geospatial raster grid data into graphs of top nodes and edges. Edges exist between nodes of neighboring ocean grid points along which vessels and physical phenomena travel. Using images for geospatial data captures local patterns but misses long-term and long-distance cross-coupled connections. Graph representation maps these complex relationships like cities connected by roads. AST/GCNs analyze both spatial and temporal changes, providing deeper insights and more accurate predictions than image-based techniques. We employed an AST/GCN using 40 days of input to predict 40 days of forecasts. This accommodates any temporal resolution, days, months, seasons, years on the input or prediction side when producing a model. This model also has the ability to support multiple features, and our methodology currently performs well, but the potential to improve scales with compute. There are several non-defense applications because graph forecasting has several use cases outside of defense, and applying these techniques to geospatial data can allow us to achieve good results in traffic forecasting, crop yield predictions, supply chain, energy grid demands, and disaster responses.
There are several benefits to the US government. Forecasted and actual ship trajectories can be compared for anomaly detection. Ship traffic volume inferred from satellite imagery can be used to forecast economic activity to detect violations of economic sanctions. The time, location of illegal ship-to-ship transfers can be predicted. And finally, this tool can combine road network topology, satellite imagery, and GMT radar data to forecast ground-moving target mobility patterns and intent. Thank you.
And next we have our final pitch from PolArctic.
We are building a tool that answers the questions you don't even know you could be asking about legal and sustainable fishing, as well as illegal, unreported, and unregulated fishing. I'm Leslie Canavera, the co-founder and CEO of PolArctic. Today, I'm walking you through our ConOps and exploring what's possible in building analytical foresight for IUU fishing. Our solution not only answers the what, but explores the vast possibilities of what if, and strategically maps out how to achieve desired outcomes. Today, I'm introducing you to PolArctic's groundbreaking program designed to transform U.S. government's IUU forecasting from predictions to actionable strategic planning across all levels of operation. Starting at the tactical level, our neural network AI architecture functions as a sophisticated analytical tool for policymaking, diving deep into the pool of ocean and global fishing watch data to retrieve fast and accurate forecasts on fishing effort. This level focuses on identifying the what in scenarios and decisions. In phase 2, at the operational level, the program integrates our agent-based modeling and digital twin framework and adopts a more dynamic approach by asking what if. This isn't about looking at the world as is, but as it could be. By generating counterfactual scenarios, it allows policymakers to explore alternative futures and understand the implications of various decisions before they're made. This is crucial in effective risk management and innovative thinking in policy formulation. At the strategic level, our phase 3, the question shifts to how can we accomplish this? Here, the program offers a strategic framework that outlines not just the end goals, but the pathways to achieving them. It's about turning foresight into action, ensuring that every step taken is aligned with a larger strategic objective. This tool isn't just technological advancement. It's a shift in thinking and solving complex problems and challenges faced by the US government at all levels. For the competition, over the course of a few days, we were able to modify our existing convolutional neural network model of 20 million parameters from a different domain to a CNN with a hyperparameter-tuned variational autoencoder in the fishing effort domain. We used PyTorch and other open source libraries to build this model. Dissemination can be via integrated data layers with an API or with graphical data layers displayed as an interactive dashboard in web pages with open source tools such as Leaflet. We are strongly proposing an improvement to this method by using our agents that will support counterfactuals as well as coordination of agents. This is currently under development in our SBIR Phase 2 grant with a completion date of Q1 in 2025. I can explain this in more detail during the questions and answers session if you're interested. While the benefits are numerous, I wanted to highlight my favorite. Our model will provide enhanced prediction accuracy. Government cannot patrol the entire ocean. Polartic's agent-based model offers precise forecasting of fish stocks and fishing activity, making it easier to target IUU fishing activities. Polartic's model provides data-driven decision-making, providing the government with reliable data to inform those policy decisions. Real-time monitoring and adaptation through Polartic's tools, we offer the ability to adapt policies dynamically in response to emerging trends and patterns. We also offer customizable scenarios through the simulation of various policy outcomes before implementation, reducing the risk of costly policy failures and unintended consequences. Thank you for your attention, and we are excited about the future and believe Polartic will significantly advance our understanding and management of marine resources globally.
As we come to the end of today's pitch event, I want to express my gratitude to all the participants, judges, and guests. Your passion, dedication, and innovative ideas have truly made this event successful. Let's continue working together to drive positive change and innovation. Thank you all, and have a wonderful day.